Let's solve the problems on least square method. So the first problem is find the matrix of projection on the line through A 1 3 2. So in this case we know that x cap is equal to A transpose divided by A transpose A. Now here, as B is not given, so the projection can be written as projection P is equal to A transpose divided by A transpose A. And when A is of course 1 3 2, it is a column matrix, and A transpose is a row matrix. When we multiply these two, we'll get 1 3 2, this matrix. So 1, this column is multiplied by these all individual terms, which results into this. And the below A transpose A is nothing but A transpose of a column matrix is a row matrix, and this is 1 3 2. So after multiplying, we'll get the result as this one, 1 by 14, it is this one. So P is always a symmetrical matrix. It is a symmetric matrix, and P square is equal to even P. So the projection on the line through A is this matrix. The next one is, let's solve the problem. Just solve Ax is equal to B by least square method, and hence find P, that is the permutation matrix, the projection matrix. P is equal to Ax cap. So A is given as this one and B is this. We know by least square method the x cap is given by A transpose A inverse. The A transpose A, the inverse of it, into A transpose B. So when we multiply A transpose and A, we'll get 2 1 and 1 2. And to get the inverse of it, we need to go for that adjoint of A. Adjoint of A, how to obtain, it's known to you. We keep these called the diagonal, main diagonal as it is, and we change the signs of this and we divide it by the matrix value. The value of this one is 4 minus 1, that is 3. And the value of A transpose B is, when we do the multiplication, it works out to be 1 1. So when we multiply these, we are getting it as 1 by 3, 1 1 after multiplying. So P is equal to A matrix into the least square, the best error we can say, the best value of X is, it is A matrix multiplied by this. So we are getting, so it is 1 1 2, and 1 by 3 is multiplied to that column matrix. Then after this, let's go for finding what is the Gram-Smith method. So orthogonal basis and Gram-Smith. So Gram-Smith has studied this orthogonality principle, and he has given some rules, as well as he has given some contribution of his own in solving this. The orthogonal matrices, if Q is a square or a rectangular matrix, then Q transpose Q is I. So where this Q is having the orthonormal columns. So orthonormal columns means this Q transpose, this is a column matrix, and Q is this row matrix. So Q transpose Q is nothing but, it is an identity matrix. So as the multiplication gives identity matrix, we can refer this Q transpose as the inverse of Q, and there are many examples for this. For example, if we have Q as this matrix, which is like cos theta and sin theta. So let's say cos theta are the diagonal elements and the minor diagonal elements as minus sin theta and sin theta. And the transpose of this one is cos theta remain as it is, just the sign changes. Once these terms get changed. When we have this, here the inverse matrix is this itself, because the matrix value would be cos square theta plus sin square theta, which is going to be 1, so adjoint is nothing but the inverse. But here when we multiply these two, Q transpose and Q, we get the identity matrix. So because this transpose matrix itself is the inverse matrix, and from this the things are like QT, the orthogonal columns, the orthogonal column matrix, the QT, or orthogonal columns Q, they preserve the length. Multiplication by Q, the Q multiplication by Q preserves the length, means the length is not going to be different, because Q transpose into Q is nothing but identity matrix, and when we multiply any matrix by an identity matrix, we are going to get the same one, so it is not going to change the thing. So we write the B as, now by using that, let's write a B. B is equal to, we can write it as B1, B2 and all, we can write this. So B can be written as Q1 transpose B into Q1, we can write, because Q transpose Q1, Q1 transpose Q1 is going to be I, so it's going to be 1. So we can write in this way, so magnitude of this B square is going to be Q transpose B. Magnitude of this B is going, this B square has to be square. Now let's see the example to understand this. If B is xyz on the xy plane, its projection is xy0, and this is the sum of the separate projections onto x and y axis. So to prove that one and to understand that one, let's say Q1. Q1 is corresponding to x axis, therefore x1, so 1 0 0, and when we go for Q transpose B into Q1, when we write this, we get this one as just only one, only first element exists. Here we can write this, so we can check this multiplication. Q1 transpose is nothing but a row matrix, and this Q1 transpose multiplied with this B, and then when it is again multiplied with Q1, we are going to get this matrix. Similarly, Q2 is corresponding to y axis, and Q2 transpose B, Q2 is going to be this, and when we sum this Q transpose, we are going to get this, and the transpose of this is going to be Q into Q transpose is going to be 1 0 0 0 1 0. So one can try this. Q1 multiplied with this Q1 multiplied with X transpose, we get a matrix, and when we multiply Q2 with this Q2 transpose, we get, and when we add them, we are going to get this matrix, and B is xyz. So from this we understand that, so Q1 Q transpose will not change any value of ours B. The B is going to be the same. When we multiply by Q transpose Q, nothing is going to be different. So now the next point is regarding, just a study is there on how we can, like how this works. So now next point is, when measurement T average is a 0. When measurement T average is 0, means it is one of the case of that least square method. So we were having the values of T as -1, 1 and 2 like that. If the average of them is 0, then how about the fitting of the straight line? The fitting of the straight line leads to orthogonal columns. So for example, if T1 is minus 3, T2 is 0, we have 3 points, T3 is 3, then the average of this is a 0. So then if the average is 0, then the things conclude that from this is 1, and this T1, T2, T3 are minus 3, 0, 3, and let's say y1, y2, y3. In those cases, what would be the values of C and D? The best values of C and D would be just 1, 1, 1, this multiplied by y1 plus y2 plus y3, because this is not going to add up anything. So in those cases, it is one of the case of least square method. So we get C cap as just a summation of y1 plus y2 plus y3, and similarly the D cap is nothing but it is minus 3y1 plus 3y3 as it gets multiplied with those values, so divided by its magnitudes. So that is one of the case. And another thing is, if orthogonal column method is much better, now from this the orthogonal column method is said to be much more better than the least square methods or even the previous methods which we have learned. So for that, even though if the T average means finding the values of the coefficients by different methods, among that when the orthogonal column method is the best one, is the prediction. If T average is not equal to 0, so in those cases it would be just a C cap and D cap that has been revised in this method. The actual main task is the Gram-Schmidt method. What is this Gram-Schmidt process? So in this Gram-Schmidt process, we consider the three vectors. Let's consider the three-dimensional system. A, B and C are the three vectors, and we go for finding the projection of it. So if there are three independent vectors A, B, C, and let's project vector V on the first one, compute. So we need to find, like even finding of the projection we want to, if we project a vector V onto the first one and compute A1 A transpose V into A. So this is also one of the method to find the values. So in Gram-Schmidt method, even we find the orthogonal vector for this matrix. So here in this method, the process followed is the Q1, Q2 and Q3 are found, and instead of knowing it like theoretically, just we'll understand the method of finding Q1 is A divided by the magnitude of A, but in finding the value of B, now in finding the value of Q2, B will come, this capital B, and which is B minus Q1 transpose B into Q1. And how it is found, we'll see in the example. Q2 is equal to B divided by magnitude of that. B is orthogonal to Q1. As B is orthogonal to Q1, we can go for finding even the third one. As B is orthogonal, we can go for finding the value of the next one, that is C. The second vector B is used in calculating Q2, and B is orthogonal to Q1. As B is orthogonal to Q1, or the component of Q2 is orthogonal to Q1, we are subtracting the Q1 component or the first axis, the first orthogonal component's value from this second one, and similarly the third one. Now to understand that, let's go for a problem. Let's see this problem. Gram-Schmidt's, suppose the independent vectors are A, B, C, let A is equal to 101, B is 100 and C is 210 will be given with three vectors. As we say, A, B, C are given to us and we are asked to find the Q1, Q2 and Q3. These are the normal vectors, or these are the orthogonal vectors of this, for this A, B and C. So let's find what these would be. So in finding Q1, what we do is, we know Q1 is A divided by magnitude of A, which will be given by A is nothing but this value divided by its magnitude 1 plus 0 plus 1 square, which gives us this, because magnitude is this one, we are getting it as root 2, so which is nothing but 1 by root 2. So we'll get this one as 1 by this value. Here A, B and C will be having like all, it may contain all the axis components or individual axis components. Now by using the Gram-Smith method, what we do is we go for finding the orthonormal vectors or perpendicular basis of this problem. So how to find that one? So for that, Q1 is A divided by the magnitude of A. So we can write it as, it is 101 divided by root 2. So we can write this one as 1 by root 2 and this value. Then how to find Q2? Then what is this first? Q1 will understand. This Q1 is, let's say we are having the three axes. So let's say x-axis, y-axis and z-axis. We know they all are perpendicular to each other. But our A is not having, it's not directed in any particular axis. It is there in, like, it is having both the components of like x as well as z. So it would be pointing in this way. And from this we have to get the Q1, and then normal to this Q1 we need to find Q2 and even Q3. So these all have to be normal to each other. So we understand the mathematical process of this one. So Q2 is nothing but B divided by magnitude of B. Then how this B is formed? This B is equal to B minus the Q1 transpose into B multiplied by Q1. So we need to write this formula. This B is nothing but whatever is given in our problem. So B is given as, it is 100. So let's use this one. So B is equal to 100 minus, it is Q1 transpose. As it is a column matrix, we'll write a row matrix. And B is 100, we'll write it. And then Q1 is as it is, this one, 1 by root 2, 0, 1 by root 2. And when we solve this one, we are going to get this. After solving, this will be as it is B, small b, and the multiplication of these will give 1 by 2 into 101. And after solving, we'll get 1 by 2, 10 minus 1. So the value of Q2 is 1 by 2, 10 minus 1. That is B divided by magnitude of B. B is this much. So divided by magnitude of this. Magnitude of this much will be, we'll get 1 divided by root 2, because when we go for finding the magnitude of this one, we'll get 1 by root 2. Sorry, it should not be there. It is 1 by root 2 itself. So this 1 by root 2 will be at the numerator, and again it will change this one to 1 by root 2, 0 minus 1 by root 2. So the value of B is this. And we can see the Q1 is 1 by root 2 and 0, 1 by root 2, and Q2 is also the similar value. It is 1 by root 2, 0 minus 1 by root 2. Now let's find the Q3. Now Q3 is C divided by the magnitude of C. Then how this C is to be found? This capital C is small c minus Q1 transpose C, Q1, and Q2 transpose C, Q2. So C value, as we already know, C is 210. We use that one. And Q1 transpose is 1 by root 2, 0, 1 by root 2. And this one, C is as it is. And again the value of Q1. And similarly for this Q2. And when we solve this, we are getting this C as it is. So after solving this first, we are getting root 2, 1 by this value, and after solving this we are getting so, and this is equal to 0, 1, 0, and as it is a unit matrix, like it is having its magnitude as unity, hence C divided by magnitude of C is Q3, which is nothing but this is same. Now for orthonormal vectors Q1, Q2, Q3 are orthogonal to Q. They are orthogonal to Q. So Q11, Q1, Q2, Q3. They are nothing but Q1, Q2 and Q3. The orthonormal vectors Q1, Q2, Q3 are orthogonal to Q. Of course, these values are 1 by root 2, 1 by root 2 and this, and these all are the Q vectors. This Q are the orthonormal vectors. Q1, these all. We'll see the next problem, that is apply Gram-Smith's process to the vectors. And to make you to understand, let's follow this process. A is a vector, B is also a vector, and C is also. But these are not perpendicular to each other, and we have to find the orthonormal basis. Means let's draw these first and then we can understand what those orthonormal bases are. So A is 1, 0, 1 means x, y, z. So it is having x and z components. Let's see the three-dimensional coordinate system. It is x, y and z. If the point is a combination of x and z, here the value of, in case of writing A was having A1, the value of this one is A is 1 and z is 1. As A is 1 and z is 1, A 1 will take and z is 1 means we have to move it up. So it would be, let's draw in this fashion. Our A is this one, it is having 1, 0, 1. Now B is 1, B is 1, 0, 1, 1, 0, 0. As B is 1, 0, 0, we can write this one as 1, 0, 0. 1, 0, 0 means it should be only x is present. Let's say it is RB. And similarly, our C is 1, our C is 2, 1, 0. As C is 2, 1, 0, we can write in this way. It is 2, 1. C is 2, 1, 0 means 2 and 1 in this way. So 2, 1, 0 means its z is 0. In this way it will be. Now these are our vectors A, B and this one is C. And we have to find the orthonormal basis to construct this. Means which should be there like orthonormal to each other, orthogonal to each other. Now by solving this problem, we got these values. Like our Q1, Q2 and Q3 are in this way. So Q1, let's write. Now Q1 is 1 by root 2 and this is also 1 by root 2. So how can we represent 1 by root 2, 0, 1 by root 2? Let's do it with a different color. 1 by root 2 means in the x-axis, 1 by root 2 means 0.7, not 7, something like that, 70%. And then 0, and then 1 by root 2 means a height, means it will be in the direction of A. Means first what we do is, while finding the orthonormal basis, we go in the direction of A itself, and this is our first orthonormal basis. Then second one is this. Second one is 1 by root 2 minus 1 by root 2. So let's represent this point. 1 by root 2 in the x-axis, but minus 1 by root 2, 0 minus 1 by root 2. Since z is minus, here it was plus. Now it will go in the bottom, like in the below direction. So this would be like almost, this would be the direction of that. X and z is negative. So this is our first Q1 and this is Q2. And similarly, in the third one, what we do is 0, 1, 0. 0, 1, 0 is this. 0, 1, 0 will be this vector. 0, 1, 0 will be this. And when we go for finding this, the angle between these would be normal to each other. So these Q1, Q2, Q3 are normal to each other. And these are the basis of that matrix, whatever is given, or these are the basis for those column vectors. So that is the theory behind those. I hope it is clear. Then the next problem, and Gram-Smith method is used in finding the orthonormal basis of the given column vectors. They may be anything. Now here the second problem is 2, 2, 1. The first V1 it is written, we can write it as A, or V1 it's left to us. V2 is this, V3. And then we have to obtain the orthonormal basis for this three-dimensional space. So for this V1, we know the formula. Q1 is nothing but V1 divided by magnitude of V1, just like A by A magnitude. So we'll write it. So this value would be, we need to write it as in terms of columns, it is 2, 1, 2 divided by 3. It should be a column matrix. It has to be, just understand it. Q2. Now to find Q2, it is B by B magnitude. So what is B? B is this one. It is 1, 3, 1, and Q1 transpose B, again Q1. So Q1 transpose is this one. 2, 2, 1. So Q1 transpose, we are finding it here. So it is 1 by 3. So this B is written minus 1 by 3, 2, 1, 2, because it is a column matrix. So we need to, these all are column matrices, column vectors. So we write that, and then 1, 3, 1 is the value of this B itself, and again Q1, when we do multiply, we get this value, and when we subtract, we are getting so. And Q2 is nothing but B by magnitude of B. When we do it, we are getting this matrix, this column. And similarly, this C, it is capital C magnitude divided by a capital C by magnitude of capital C. It has to be found with this formula. So here we are finding it by substituting these all values, and it works out to be minus 5 by 18, this minus 5 by 18, and 10 by 9. And in this way we can write Q1, Q2, Q3 in this way. It is our Q1, Q2 and Q3. These are the three bases of that. These are the three orthogonal bases or orthonormal vectors of these columns, which are given as 2, 2, 1, 1, 3, 1 and 1, 2, 2.